In this series of talks, we are going to learn about automatic speech recognition. Human beings communicate with each other mostly in verbal mode by speaking to each other. Humans generate speech sound using a production system and listen using ears, and they understand using the human brain. The goal in automatic speech recognition is to teach a machine to do the same thing. That is, to listen to speech sounds and make meaning out of it so that it can take appropriate action. There are several models of doing the speech recognition by machines. Some of the three-letter acronyms are dynamic time warping, Gaussian mixture model, hidden Markov model, deep neural network. We are going to touch each of them in this lecture series. This is the outline of the series of talks. Initially, I will talk about the processing of the speech signal, which is an audio signal, to extract information from the speech signal, the information that is useful for recognizing the sequence of sounds, that's the speech. The well-known speech feature are called Mel frequency capture coefficients. And then we will talk about various techniques of recognizing speech. To begin with, we'll learn how to recognize one speech sound, and we will also talk about statistical models, probabilistic models. Gaussian mixture model is an example that we will take. Then we talk of recognition of not just one sound but a sequence of sounds, for example a word, using a model called dynamic time warping that takes care of the speaking rate variations and things of that time. Then we will move on to a better statistical model called hidden Markov model that recognizes not just a word but a sequence of words, a sentence, an utterance. We will learn about recognition using a trained hidden Markov model and how to train hidden Markov model using speech data whose transcriptions are known. At the end, we hope to learn about the current popular mode of speech recognition, which uses neural networks, a rough, simple-minded model of how our human brain works, the artificial neural networks, specific one particular version of it, which is called deep neural network, which has several layers of neurons, in conjunction with the hidden Markov model. At the end, we will also talk about language models for speech recognition, because so far most of these models concentrate more on acoustic models, recognizing speech sounds. From the sequence of speech sounds, using the rules of grammar, we recognize an utterance, and that is called the language model. It is language dependent. What is automatic speech recognition? Somebody speaks, he has a concept in his mind, he chooses a particular language, say English, constructs a grammatically correct sentence, and then speaks the corresponding sequence of sounds. So from his mouth comes the waveform, which may look something like this. So this is the input to a machine, which has to recognize the original concept. So this speech is a sequence of sounds, so its properties vary with respect to time. So we take short segments of speech called frame of speech, such as this, and extract some use characteristics which will help us to recognize the identity of the sound, whether it is a, ka, ta, and so on. And so that process of signal processing to extract set of features is called parameterization here. So if we do this every, let's say 10 milliseconds, so if we have a second of speech, we get about 100 a sequence of 100 speech vectors. The job of the speech recognition models is to use this sequence of speech vectors to infer the original sequence of symbols. Okay. So there is a message here which is encoded in the speech signal, and the job of the speech recognizer is to decode that message. That is the speech recognition. Speech recognition is one instance of pattern recognition. In fact, it is a recognition of a sequential patterns because speech is a sequence of sounds. This is a block diagram of a general pattern recognition, so-called supervised pattern recognition, where the input is the pattern, which may be written pattern such as the letters in this slide, or audio patterns such as the sequence of speech sound that I am talking. That is the input, called it a signal. In particular, when you are talking about speech signals, time varying information. So we do the signal processing to extract some useful features, and using these features and taking a large amount of exemplar patterns, we build models for different patterns. In the case of speech sounds, we build acoustic models for each of the sounds in our language. So this is the phase, so-called training phase, where the system is taught. It is like teaching in a class. The system is taught the properties of the various speech sounds, and it estimates the parameters of the mathematical models representing the speech sound. Then the model is ready, which is ready for use. That phase is called testing phase, and an input comes, audio file is given, and the audio file goes to the same signal processing as it was in the case of the training phase. The sequence of feature vectors are matched with the models of the various speech sounds to recognize the sequence of sounds. So in speech recognition, our goal is to recognize sequential patterns, sequence of sounds, from the reference templates of the models. Reference templates of the models are trained during the training phase. Let's look at a time waveform. This is a display of a speech sound. The word that was spoken was Tiruvant. So on the x-axis the time in seconds, on the y-axis is the amplitude in some digitized form. So you see that this is the word Tiruva. Ta is here, E is here, R is here, U is here, W, A, N. In this particular sound, there are three vowels: E, U, A. E, U, and A. If you look at this time waveform, which is the input signal to the system, it's very difficult to distinguish between these three sounds. They appear similar. Therefore, it is better to do the analysis in another transform domain. It is better to analyze the frequency property of these vowels. Therefore, we perform frequency analysis, and we perform in this particular waveform, let's say up to 0.4 seconds. There is silence here, there is a ta here, there is a e here, r here, and so on. Therefore, we take short segments of speech waveform and perform the analysis. Such an analysis is called short time processing of the speech signals. So, typically, we take segments whose size is 25 millisecond, 25 by 1000 millisecond. And take this segment in this particular sound. In this particular case, suppose it is this particular frame is 25 millisecond duration waveform. You cut it out and analyze it, do a frequency analysis, find out its properties and so on, and then you move your frame, analysis frame, by 10 millisecond and do the similar analysis of this segment of speech. Every time you keep shifting this frame by 10 millisecond. So every 10 millisecond you extract properties of that particular segment of audio, which will help us to distinguish what speech sound it is. So the shift between the time interval between the beginning of successive analysis frames is called frame shift. It is 10 millisecond. Therefore, if we have 1 second of speech, we will get about 100 speech frames, and correspondingly we get a sequence of 100 speech vectors or set of speech attributes. What kind of analysis should we do? We said we will do the frequency analysis. It is good to estimate what kind of properties should we see in this frequency spectrum of speech sounds based on the knowledge of how sounds are generated by human beings. So this is a schematic of the production of the speech sound by humans. Quite often I borrow slides from various people. I give the source here. So when we want to, normally we breathe in and breathe out. The nose is open. There is a apparatus called glottis which is open. So the air goes in and out without any obstruction. When you want to speak, the brain gives commands to the muscles that controls this vocal apparatus, and that closes. So it stops the flow of the air. Initially we breathe in, there is air in our lungs, and that is the source of energy. So the tension of the muscles that control this glottis, the glottis is the area between these vocal cords or vocal folds. The tension in this is kept in such a way that when the pressure of the air from the lungs is a little high, this opens and air flows through this area which is called the glottis. When air flows through a narrow area, Bernoulli effect comes into picture. The pressure in this narrow area reduces, and the tension in the vocal folds is kept such a way that when the pressure reduces, these vocal folds come together and the passage of air is blocked. It's like a gate is closing again. This process, and then the air pressure from the lungs increases, gate opens, closes. So vocal folds keep opening and closing. This is called vocal fold vibration. So as a result of this, puffs of air comes from the lungs to the air cavity above the glottis. This is the voice box, as is called, the kind of bulge that we see here. That is where the glottis is, and from there the puffs of air or pulses of air, packets of air come through to this air cavity and comes out through the mouth. So these pulses of air excite the air cavity here, and this sets up resonances in the air cavity in the vocal cavity. So this air cavity is called vocal cavity because that is responsible for generation of voice. Now, the size and shape of this vocal cavity determines the property of the frequency property of the speech that comes out of here. The input to the signal is a periodic waveform as is shown here. This is the amount of air that goes out as a function of time. But because of the size and shape of the air cavity and the resonances that are set up, this waveform that comes out looks something like this. This vocal fold vibrates several hundred times a second. For example, the frequency with which I am speaking now, the vocal cords are vibrating at around 130 hertz. 130 times per second. It's vibrating, opening and closing so quickly. This normal terms we call it as a pitch frequency. The pitch frequency is actually a perceptual phenomena, but quite often we use them interchangeably. Pitch of female speakers tension is higher, therefore the pitch is higher, typically 300 hertz. Pitch of children can be as high as 500 hertz too. So a sequence of pulses or packets of air is modified by the resonance of the air cavity, and the output comes out of speech. We digital communication engineers would like to model this as a digital filter. This is the source which which is a sequence of pulses, excitation source, and this is a digital filter. We model it as the all-pole model. Most of the time that works with the reasonable approximation. And the different sounds are characterized by the frequency transference characteristics of this air cavity. So here is the the way, as this is the time as the horizontal axis. The vertical axis is the amount of air flow. When the glottis opens, air amount increases, and when the pressure between in the glottis between the vocal folds reduces, the glottis closes. Suddenly it closes, and it keeps the vocal folds are closed together for some time. When the pressure from the pressure of the air from the lungs increases and opens, closes, and so on. So this phase is called open phase, and this is called closed phase. During the closed phase of the glottal vibration, the resonances do set up in the air cavity because there is no external disturbance. The energy has already come, and the system, the air cavity, it settles down to its resonance frequencies, and we see this kind of waveform. That waveform, its characteristics represent the size and shape of the cavity. This is the case of the vowel, the first vowel of Indian alphabet, Indic alphabet A, for example. What we can do is make some simple model. We are scientists, we want to predict what could be the frequency characteristic of such an excitation. So in the case of the simple sound such as A, what we do is make a simple model. When you make models, it's a mathematical description. It can be crude, and we take the simplest model here, which we assume that when the glottis is closed, its resonance is set up. This tube from here to here, it is actually in L shape, it's bent in various size shapes, so that we assume that it is a tube of uniform cross section. So we assume that the tube is closed at the glottis, open at the lip, and its cross sectional area from here to here is uniform, is constant. It's a gross approximation, but still this simple model gives us some estimation of the frequency characteristics. So what could be the proper characteristics of the sound A, and then we will compare this with the actual frequency characteristics of the sound vowel A, and see how do they compare. So if we make that, such a model is called uniform tube model, and you can use the physics to estimate the frequency of the fundamental frequency of vibration, lowest frequency at which it can vibrate. The fundamental frequency of vibration can be estimated assuming 340 meters per second as the speed of sound in air, and assuming that 17 centimeter is the length of this vocal tract from here to the lips. It turns out to be around 500 hertz. In fact, it not only does it vibrate at 500 hertz, but it also vibrates at odd multiples of 500 hertz, 1500 hertz, 2500 hertz, and so on. So this is what a simple physics model tells about the frequencies of such a model of the vowel A. Of course, we engineers model it as a digital filter. There is a source of excitation, that is the lower graph on this curve, and output comes the speech waveform, and we model this as a filter. And since there are resonances that are more important, we quite often model it as a pole of a filter. So source filter model, we have input is glottal vibration, vocal tract, and output this vocal tract size and shape determines the output speech waveform. When you speak different speech sounds, when you say A, E, U, A, O, I keep changing the size and shape of my vocal tract, and that means the filter characteristics do change. Well, if we look at the basic principles of the digital filters, we say that if the excitation sequence is given by E of n, where n is the discrete time instant, n, and the filter is characterized by the impulse response function, the output signal S of n is the convolution of the excitation sequence and the impulse response function. If you go from this time domain indicated by the index n to the frequency domain indicated by the discrete frequency index k, so this convolution becomes a product. So the spectrum of the speech signal, that is the output, is the product of the spectrum of the excitation and the product of the system and that of the system response function. This is a product. So if you take a logarithm of this equation, that becomes a sum. So log power spectrum of the speech signal is the sum of log power spectrum of the excitation and the log power spectrum of the filter. Log power spectrum of the filter, we already estimated that log power spectrum of the filter should have a peak at 500 Hz, at 1,500 Hz, 2,500 Hz, and so on. And let us see what should be the log power spectrum of the excitation. Excitation is a periodic pulse. What is the periodicity? Let us say the time interval between this and this is 5 millisecond. Then 5 millisecond is the periodicity. So the frequency is 1 over 5 millisecond, 200 Hz. So in the spectrum, if you look at the spectrum, here is a spectrum plot, frequency along the x-axis and intensity in the decibel scale is the logarithmic scale on the y-axis. In that case, we should see, because the periodicity is 5 millisecond, we should see a peak in the spectrum at 200 Hz. So this is 1000 Hz, this is 200 Hz, we see a peak in the spectrum. So notice that this periodicity is 5 millisecond, it is not a sine wave, therefore not only will you see a peak at 200 Hz, but also at its harmonics, integral multiples of the 200 Hz. So you should see a peak at 400 Hz, 600 Hz, 800 Hz, 1000 Hz, and so on. So this is the fundamental frequency, and these are the harmonics. The amplitude of the harmonics decreases with the time. So the source power spectrum, it's a decibel scale, that's a logarithmic scale. So the log power spectrum of a glottal vibration should appear like this, assuming that the fundamental frequency of vibration is 200 Hz. So that we know how this looks like. We also saw how this looks like because it should have a peak at 500 Hz. So we said that not only should it have a peak, if you assume that the vocal tract or the filter is a tube of uniform cross section closed at the glottis end and open at the lip, the peak should, the first resonance peak should occur at 500 Hz for the case of the vowel R, and its odd harmonics. The odd harmonic requirement comes because the tube should be closed at one end and open at another end. That's the requirement. The amplitude vibration should be maximum here and 0 here. That's the requirement. Therefore, the another peak should occur at 1500 Hz, 2500 Hz, and so on. So we know the log power spectrum of the excitation, we know the log power spectrum of the filter, and according to the digital equation, the log power spectrum of the speech should be the sum of the log power spectrum of the excitation and log power spectrum of the filter. So it should be sum of this and this. It should look something like this. When you add these two amplitudes, this gets modulated by these peaks. So we expect the log power spectrum of the speech signal to appear like this. Here is the time waveform, here is the corresponding spectral information in the spectrum. Now let us look at the spectrum of the vowel A to see whether the spectrum indeed appears like this. So here we are showing the spectrum of not vowel A but the vowel E of the word Tiruva. And so here's the spectrum 0 to 8 kilohertz, 8000 hertz, and the power on the y-axis in decibel scale. What you see here is that we see some smaller peaks here which are due to the pitch harmonics. Let's look at the yellow curve, which are due to the fundamental frequency of vibration and its harmonics. In addition to that, modulating E are the some major peaks in the spectrum, peaks which occur somewhat far away. So this spectrum does indeed look like this spectrum. Minor peaks, peaks that are occurring frequently due to the pitch and its harmonics, kernel frequency and its harmonics, and slow modulation of this line spectrum because of the resonances in the spectrum. The resonances are not at 500 and 1500 and 2500 because that is for the case of the vowel A, and if you take the case of the vowel E, the resonance occur at around 300 Hz and some 1900 Hz and so on. So the simple model that we used of a uniform tube model also gives some information, and it roughly matches our prediction of our mathematical model roughly matches with that of the spectrum that is the green curve there. Okay. All right. This is what we predicted. Now, so that is the situation if the frequency is 200 Hz. This is this is maybe a female speaker. A male speaker, his fundamental frequency vibration is smaller, pitch is smaller, 100 Hz. If the fundamental frequency vibration, pitch frequency is 100 Hz, the peaks occur at 100, 200, 300 Hz, 400, 500, 600, so on. Within 0 to 1000 Hz, there are 10 peaks. In contrast with a person whose pitch frequency is 200 Hz, where there will be only 5 peaks in the interval 0 to 1000 Hz. But let's assume that both persons speak the vowel A, in which case, according to our theory, the spectrum of the speech spoken by the person whose pitch frequency is 100 Hz should look like this, and the spectrum of the same vowel A spoken by another person whose pitch frequency is 200 Hz should look like this. You see that there is some similarity between these two log-power spectra of the speech sounds as tokens of the same speech sound A. The similarity is the peaks do occur at 500, 1500, 2500 in both cases, but there is some variation. Variation is because of the pitch frequency. Our goal in speech recognition is to recognize speech sounds, not whether the vowel A is spoken with pitch frequency 100 Hz A or with the high pitch frequency A. I can change the pitch frequency. Even if I change the pitch frequency, whether I say A or A, in both cases we want the system to output the same symbol A. In other words, we want the computer to ignore the pitch frequency when it comes to recognition of the typical speech sounds, largely speaking. Therefore, our signal processing should have the capability to ignore these variations in the spectrum, sharp variations in the spectrum. Whether it is varying sharply or whether it is varying slowly, we need to ignore the influence or the effect of the. Now suppose you look at either this or this and you want to smooth it. Look at this as another pattern, another signal, something that I want to smooth. When you want to smooth a signal, normally what do we do? We pass it through a low pass filter. So the goal is to smooth these spectrum which has pitch ripples and broader peaks due to the format. So let's look at what involves smoothing a curve which has slowly varying components and rapidly varying components. Let us illustrate it by smoothing this brown curve which has rapid variations as I may handle and slow variations. So it is the sum of rapid variations, the blue curve, and the slow variations, the green curve. This is the sum of this and this, and if we want to smooth this to retain slowly varying component and to ignore or minimize the effect of rapidly varying component. Suppose such a curve is there. So if you take a Fourier transform of this, what will you see? If you take a spectrum, frequency spectrum, what will you see? This is a rapidly varying component. So if you take it alone, it will have a peak at a higher frequency. This is the spectrum at a higher frequency. If you take on the other hand, if you take the other component, slowly varying component, green curve, it is slowly varying, therefore its frequency is smaller, therefore the peak occurs at a lower frequency, because this is the origin of the spectrum. On the other hand, if you look at the brown curve, which is the sum of these two curves, then in the spectrum of this brown curve you see both the peaks. The peak here is larger because the amplitude of variation is larger, but otherwise the positions are different. Our goal is to retain the slowly varying component. So from the spectrum of the brown curve, which has both the peaks, our goal is to retain only the first peak or the initial peaks. These correspond to slowly varying components. So if you want to do that, what you will do? You just retain all these values as it is, and later values you set it to 0, which is equivalent to multiplying this spectrum, power spectrum, by a square function like this. It's nothing but a low pass filter. So if you take a curve which has slowly varying component and rapidly varying component, your goal is, if the goal is to smooth the curve, you take a Fourier transform, retain only the first few coefficients, set all the other coefficients 0 coefficient you don't have to remember because they don't carry any information, just retain the first few coefficients. This analysis is called Kestrel analysis. This processing is called Kestrel processing. Kestrel is essentially inverse Fourier transform of the log power spectrum. Now since our spectrum that we had is this green curve which has this rapidly varying component and slowly varying component, if you look at this. So that is what we get, this green curve at the end of the log power spectrum. You take a Fourier transform, retain only the first few coefficients. Those first few coefficients essentially represent the purple curve, the slowly varying